How do these related rates show up in calculus then? And how does it connect to the chain rule? So I've given you an example here. We have a cube, and the volume of a cube is equal to, the volume is equal to the side length cube. So this is just giving you the definition of the cube. And we have this cube, and its side length is presently 9 centimeters. So it's a 9 by 9 by 9 cube. And what's going to happen is this cube is dynamic, so it's going to change size. So we want to know how fast is the volume changing? In other words, what is dV by dt if the side length is changing at a rate of 6 centimeters a second. So the side lengths are increasing at a rate of 6 centimeters per second. So the volume is going to increase as well, but by what rate is it increasing? And I want you to notice something here. If I just differentiate V, I would just end up with dV by ds, which is 3s squared. Well, that's true, but that's not actually finding out the rate of change with respect to time. It's finding out the rate of change of volume with respect to the side length. So we need to do something slightly different. Now, we want to introduce this factor of time, which does not show up in the original formula. And to do this, we just take the original function and we're going to differentiate v with respect to time. What that means then is, if we differentiate with respect to time, we would have to first differentiate with respect to the side length. And then because the side length is a function of time, it's an embedded function, so then we multiply using the chain rule. We multiply by ds by dt. And if you take a look at the units here, these units are consistent because, yeah, they cancel out. This is really dV by dt if I put it all together. But we can find the parts separately. I already know what ds by dV by ds is. I calculated it up here. I figured it out. Okay, I just differentiated, but it was with the wrong variable. Differentiating with respect to time, well, it's not the right variable, but I can do it correctly as long as I apply the chain rule to generate the ds by dt. So how does it work? So I'm going to show you how this works. So when we differentiate this, when we do this problem, the first thing is we first need the relationship for volume and side length. We need to connect that together. So we have that to start with. But instead of differentiating with respect to side length, we differentiate with respect to time. Okay, so it looks like this. We start with our volume expression. Volume is equal to side length cubed. We do dV by dt. We're going to differentiate this side with respect to time. That's what we want. But to do that, we need to first of all differentiate the s cubed, which is really dV by ds. But because s is a function of time, we need to think of s as an embedded function and apply chain rule, ds by dt. And algebraically, yeah, we have dv, the ds's cancel out, and we have dv over dt on the left side, over dt on the right side. But now we have an expression that has dv by dt. And furthermore, we have already established that ds by dt is 6 centimeters per second. We've already established the actual value of the side length. Okay, so I'm just going to highlight this here. The s value is 9. The s value is 9 centimeters. So I can actually just replace the 9 centimeters in here. And I can just plug in the different parts and I can calculate dV by dt. So it looks like this. So I have my dV by dt, which I'm looking for. I want to know how fast the volume is changing with respect to time. I have 3s squared. Okay, all that, just so that we're clear, that all that is my dV by ds. Okay, and then inside there, my s was determined to be 9 centimeters, so I'm going to put 9 centimeters into here. That's my s value. I need to multiply that by the ds by dt. That's the change in side length over the change in time, which was 6 centimeters per second. And I need to then just calculate this out. Now notice that the units all work out. We end up with centimeters squared times centimeters, which is 70 centimeters cubed per second. That's definitely the units for change in volume. I'm going to do 3 times 6 is 18 times 81. 18 times 81, I think it's 18 times 81. We're going at with 1,458 centimeters cubed per second. Okay. Okay, so that's the rate of change of the volume with respect to time if the side length is changing at 6 centimeters per second and the size of the cube is 9 centimeter cube. So it's a 9 by 9 by 9 centimeter cube. 9 by 9 by 9 cube.